we have everybody, so we can get started again because we're starting late. I'm guessing we're going to end a little late. We'd like to have Chuck Horowitz talk to us about crust physics and how it connects to both experiment and observations.
Great. So this is, I think, the third talk I've given in 9 days. Unfortunately, my talks are reflecting more and more my teaching philosophy, which is almost in time. So I've more or less finished this talk. Now, so I want to talk a little bit about crust physics, as Sanjay said, but I always want to include some experiment. So I'll say a little bit about the PREX experiment, which is measuring the neutron radius of lead-208, and that has implications for the structure of neutron stars. Talk a little bit about nucleosynthesis during mergers, what's actually going on in this ejected material, and the material is going through these nuclear pasta phases before it becomes nuclei. So I wanted to talk about that. So we'll have some molecular dynamic simulations of nuclear pasta, which are the complicated shapes at the base of the crust. And then I wanted to end talking about more conventional crust where you just have ions, and in particular the strength of neutron star crust. So please interrupt and complain as we go along, but maybe that's redundant. So I want to talk about actually measuring the thickness or the size of lead-208. Where are the neutrons? Well, we can use parity violation to isolate the neutrons. So the Z boson couples to the weak charge of a nucleus. The weak charge of a neutron is big. The weak charge of a proton happens to be small. So the weak interaction at low q squared, low momentum transfers, probes the neutrons. So experimentally, what one actually measures is this parity violating asymmetry. It's the fractional difference cross-section for scattering positive helicity electrons or negative helicity electrons. It's the weak interactions. This is of order a part per million. It's a small asymmetry. It's coming from the interference between the weak amplitude and photon exchange. So in Born approximation, the weak amplitude is related to this form factor, the Fourier transform of the weak charge density at the momentum transfer of the experiment, so it can, in principle, map out the distribution of weak charges or neutrons in a nucleus. Difficult experiment, but this electroweak reaction is free from most strong interaction uncertainties. Okay. So here's what a nucleus looks like. Just look at the dashed lines. This is lead-208, a simple relativistic mean field model. Density versus radius, the surface is out at 6 or 7 Fermis. So the try that again. The red dashed line is the proton density. There are 82 protons in lead. And the black dashed line are the 126 neutrons. And what the experiment is, measurement at a single low q squared, is probing how much the neutrons are expected to stick out compared to the protons. So if you go into the skin of a heavy nucleus, we expect it to be neutron rich. Okay, just very quickly, the experiment involves almost all of Jefferson Lab, electron accelerator in Virginia, intense polarized source. The electrons are accelerated down and back to 1 GeV, strike a thick lead foil target. The scattered electrons are collected into large spectrometers. Let me just emphasize all these beam monitors are very important for controlling systematic errors. Experiment ran in 2010. 1 GeV electrons elastically scattered from a thick lead foil. the measured parity-violating asymmetry, 0.66 parts per million, with a relatively large statistical and small systematic error. From this measured asymmetry, I inferred that the neutron skin thickness in lead, the difference between the RMS neutron and proton radius, is about 0.33 Fermis, but unfortunately this large error bar reflects primarily the statistical errors of the experiment. So our future plans are to run again. PREX-2 was approved, probably was scheduled to run probably in 2016, to run lead again to accumulate more statistics and decrease that error bar by a factor of 3. In addition, we are also approved for a second experiment, CREX, to measure the neutron radius of a smaller neutron-rich closed shell nucleus, calcium-48. Okay. Measuring the neutron radius allows us to infer the pressure of neutron-rich matter. The pressure is forcing neutrons out against surface tension. If the pressure is high, you expect a large neutron radius. So Typel and Brown showed a strong correlation between the pressure of neutron matter, pure neutron matter, at say 2/3 of nuclear density, some average of the surface and the interior density. So the pressure at that density and the neutron radius in lead. So here's a calculation, the pressure of pure neutron matter versus density. This is normal nuclear density, 0.16 nucleons per cubic Fermi. The blue band are chiral effective field theory calculations of Kai Hebeler et al. That include chiral 2-nucleon and 3-nucleon forces. The calculation with only 2 neutron forces yields a significantly lower pressure. And then we can plot the preliminary PREX result, assuming this Typel-Brown correlation, and it suggests a relatively big pressure for neutron matter, but the large error bar is certainly consistent with the Hebeler et al. Calculations. Okay, so the experiment is probing the pressure of neutron matter at subnuclear density. This slide is very much over the top, but it makes a point. I think you'll get it.
So I just want to make a comment about the previous slide. So there is an error bar that's indicated for the theoretical calculation in blue, but there is still debate about the size of that error bar.
I have no argument with that. The good news is they at least included an error bar. Actually, let me, I will say something. Up to what density do these chiral effective field theory calculations converge, I think is an open question. It's an important question. The hope is they converge up to around normal nuclear density, but maybe not.
And Chuck, have people looked at the corrections to PREX? I mean, it's one goes...
Corrections? Oh, excuse me.
But there's parity violation in the target, and you know certain kinds of corrections grow with A. Have you looked at?
Yes. A lot of things go away because it spins 0. So any parity violation in the target. The biggest correction is Coulomb distortions. It's about a 30% correction. Meson exchange currents tend to be very small just because lead is big. So there's a large paper we wrote over 10 years ago now where we tried to at least list all the corrections we could think of. Okay, so Galileo's crime was to suspect that both the laboratory and the heavens are made of the same stuff. So for right now, let's talk about neutron-rich matter. In astrophysics and the laboratory, it has the same neutrons, the same strong interactions, and the same equation of state. So if you measure in one place, be it astronomy or in the laboratory, it has important implications in the other domain. Okay, so one way to say that is we just want to compare the radii of two different isotopes. I've talked about measuring the radius there, and fortunately I was away last week. You guys were spending a while talking about measurement of neutron star radii. One way to think about it is this radius is the pressure of neutron matter at relatively low density, around 2/3 of nuclear density. The radius of a neutron star, Jim Latimer and others, have shown it's sensitive to the pressure at medium densities, say 2-ish times nuclear saturation density. And then the maximum mass of a neutron star is most sensitive to the pressure at high densities. So if you have those three different observables, you can probe the pressure at different densities. Okay, and to get into trouble, I wanted to mention just one group's measurements of neutron star radii. I like showing this because Gillette et al., I believe, make their assumptions explicit, and these are a relatively simple set of assumptions. So they assume that these neutron stars in globular clusters have non-magnetic hydrogen atmospheres. You can agree with that or not, but at least it's an explicit assumption. And I would say further, they try to make it self-consistent. They try to actually calculate the composition of the atmosphere and how there's enough hydrogen left that quickly rises above the more dense stuff to form the hydrogen atmosphere. So they have at least a self-consistent argument why the atmosphere should be hydrogen. Clearly, spherically symmetric is important. And then they get a very small radius. So the radius, say 10.4 kilometers, is the upper limit at the 90% level. So I just wanted to try to put these three classes of measurements on the same plot. So this is mass versus radius of neutron stars. So we see two solar mass neutron stars, so the equation of state has to go up above that line. And then here's the Gillette et al. 10.4 kilometers as the upper radius of a neutron star. So if that's correct, then you have to go to the left of that line. Clearly there's great tension between this and that. They're barely consistent, and the only way to accommodate both is to have a low pressure at low density, say nuclear density and somewhat above, to get down to this radius, and then you have to rapidly stiffen to get up to that maximum mass.
So Chuck, last week we heard a nice talk about why this tension may not be significant, because the companion, there's suggestive circumstantial evidence that the companion for that object has helium.
So last week I was talking to Bob Rutledge, and he was arguing that even if it's a so-called helium star, all the models of helium stars still have enough hydrogen, and then he calculated how fast you should burn away that hydrogen. He can't, even with a very small hydrogen fraction, he can't get rid of the hydrogen fast enough. So he has a self-consistent model even for that helium star that leads to a hydrogen atmosphere.
So there are observations that indicate that there is hydrogen present in the star?
Well, all models of helium atmospheres have residual hydrogen at some level.
All models?
No.
Yes.
Wait, what? Say that again?
All, what was the right word? Self-consistent models. So if you build the atmosphere out of burning something, evolving something, there's still a little bit of hydrogen left.
So how much is a little bit? How much? I mean, I'm going to go.
10 to the minus 5.
Okay, so if 10 to the minus 5 can do it, it may be hard to.
Wait, 10 to the minus 5. Mass fraction.
Mass fraction.
So even if the helium white dwarf has a tiny 10⁻⁶ mass fraction of hydrogen, it's enough to make a photosphere. Once you account for gravitational settling, you don't need very much mass just to make a photosphere's worth of hydrogen.
And it's not me to resolve this argument. The comment I made is that their work has sort of a self-consistent model that it would be a hydrogen atmosphere. So they're trying to calculate the composition of the atmosphere, and they get hydrogen from their calculation.
Chuck, it should be pointed out that if they relax the assumption that all neutron stars have the same radii and analyze each of the sources independently, they get radii ranging from 8 kilometers to 20 kilometers.
Uh-huh.
Yeah, I mean.
But that's neither here nor there.
The small radius is based on, I said this last week, but it's based on 5 sources,
Mm-hmm.
and it's strongly biased to the smallest one, 6397. And if you take that one out, then the radius moves up to 10.7.
So
You're arguing with the wrong person. Their work, they present what they claim are self-consistent error bars. They have done the analysis where they remove one source.
Yeah, I mean, this is from their paper.
Yes, no, I understand. I understand.
We're just trying to understand if this tension is really that significant.
and so I just checked.
Let me make the point I want to make, because it's not for me to resolve
So
what.
I just want to point out that the comment you said where Bob Rutledge says there's still 10⁻⁵, fraction of hydrogen, not in the stellar models of Alex Hager. I just checked. So in his case, the hydrogen abundance goes down well below 10⁻⁶. So you could get a pure helium. It's not pure helium. It has other abundances.
Yeah.
Heavier on. It's not.
I mean, if you have a model and you run it and you get no hydrogen, that's useful. I mean, that's what I'm saying. Bob has a model that he takes and he finds the hydrogen. That's all I'm saying.
And we have to be careful throwing around these numbers. I mean, 10⁻⁶ sounds very small, but I only need 1 gram per square centimeter.
Yeah.
Right. So
Alex says goes down to 10⁻⁶ and then it goes to 0 in the helium layer. So it's less than 10⁻⁶ because he kept track of it at 10⁻⁶ level. So you can throw it in there, but I'm worried that if you just want a low radius because it says something interesting, you're pushing things.
This is really great. I just threw in one slide and I got to avoid giving my whole talk.
But you did that on purpose.
That's just what I said.
Exactly. He said, I'm going to show you this, because you were pointing out, then I could go sit down.
Let me quickly make the point I wanted to make here and then run. So these brown lines are the central density of these stars. They may be somewhat model dependent, but at least roughly. So if you have really low mass stars, their central density is around ρ0. So I went down to ρ0, and for these models, they have different pressures of neutron matter at ρ0, and they're correlated strongly with skin thickness in lead. So we could plot the PREX result here, and a high skin or a thick skin is a big pressure. And so clearly if you had a big pressure here and you got to support a large mass there, then there's no way to get...
There's a conflict between this slide and the previous one where you show that the NN interactions give a neutron skin thickness that's much smaller than 0.15.
Let me go here. You have to be careful on whose NN.
Okay.
And also, the comment I was going to make is that the bones of this slide were photoshopped by Vitek Nazierovich, and these points here might not be exactly in the right place. So if the radius is really that small, then it's all but unavoidable that you're going to have a relatively thin skin in lead. Okay, so there, at least in one slide, you have laboratory measurements here, radius measurements there, and mass measurements up there. Okay, so now, an hour and a half after I started, or was supposed to start, let me start my talk. I wanted to do some nucleosynthesis. I just came from a symposium in honor of Paul Soder's 70th birthday. He's a remarkable parity-violating electron scattering experimentalist who has single-handedly, or almost single-handedly, over 30 years, dramatically advanced the field of parity violation. So my original plan was to give him a gold watch, but I'm too cheap. Instead, I was hoping you guys could help me help Paul locate the source of all the gold in the galaxy. Okay? So half of the Helmy elements, including gold, made in the R process. The wonderful question, the right question, we should have asked this 20 years ago, is simply what makes all the neutrons that you need for the R process? That's what we should have been talking about for a long time. So let me give you two possibilities. Neutrinos, the ratio of neutrons to protons in neutrino-driven winds are set by the relative rates of neutrino and antineutrino capture. So I've got a lot more to say about neutrinos, but I was going to actually talk next week, and so I was going to talk about neutrinos then. So another possibility is gravity. You simply compress stuff, you make it neutron-rich. Neutron stars are 90%-ish neutrons, just from the high density. Of course, the problem is you live by gravity, you die by gravity. If you use gravity to compress things, you have this problem of how do you get the stuff off of a neutron star. And so we've talked a lot about matter ejected, for example, by tidal forces. And so nice talk yesterday about how matter can be ejected during these mergers. I want to follow a fluid element in, for example, a tidal tail as it decompresses. The remarkable results, we believe this matter is so neutron-rich that it undergoes a robust R process. So there seems to be little nuclear physics uncertainty in what the stuff makes. And so the R process yield is, I like to think of it as two numbers, how much material is ejected per merger and what is the merger rate. So we've had a bunch of discussion about that. So let's just follow a fluid element. And one of the things the fluid element does is it makes nuclear pasta. So during the neutron star merger, you're decreasing the density. You can start out with uniform nuclear matter in the core of a neutron star near the crust core boundary. As it's being ejected to lower density, it forms complicated nuclear pasta shapes, which then react to form nuclei and neutrons, and then the neutrons capture to give you an R process. So nuclear matter at somewhat below normal density forms these complex shapes just because of competition between short-range nuclear attraction and long-range Coulomb repulsion. So I'm just going to have a simple semi-classical model. So I have nucleons interacting with the potential, short-range phenomenological nuclear potential. It's attractive at intermediate distances, it's repulsive at short distances, and the parameters here are adjusted to reproduce nuclear saturation. So that's saturation density and binding energy of nuclear matter. And then you just have Coulomb between the protons. We don't follow the electrons explicitly in our simulation, but the slightly polarizable gas of relativistic electrons give a screening length. So actually it's a Yukawa Coulomb interaction that's been screened by the electrons. Okay, and this semi-classical simple MD model is very easy to run on a computer. We can do big simulations. We are now doing a simulation with 3.3 million nucleons, and we can run for large simulation times. So I wanted to show you one simulation. It's a movie. Andre Schneider prepared this. There's 51,000 nucleons in a box. Temperature is 1 MeV. And we slowly expand the box. So it's 80 Fermis across to start with. And in a few thousand core weeks of computer time, the box is expanding to about 200 Fermis on a side. And so as it's expanding, the density drops. So you're looking at thermal fluctuations. The little brown spots are lower density. So the matter wants to stay at normal nuclear density. So as the density goes down, it forms these voids. Coulomb keeps all the voids from merging in a simple way. So you get lasagna plates. And then as the density goes down further, the lasagna will break up into spaghetti, into rods. So again, you're thinking of matter expanding to lower density during a tidal tail in a merger. So now you have these rods, and then the rods fission into nuclei. Okay, so there are now nuclei, and so not shown is the neutron gas between the nuclei. What's plotted is actually contours of the proton density. If you keep expanding for a while, then a graduate student, Matt Kaplan, counted the number of nucleons in each cluster. And so here the distribution of mass number for the various nuclei. And I should say, just look at the bottom panels. These are for different proton fractions. The temperature was 1 MeV. And so you get these mass 150 or more type nuclei. And actually these distributions are very close to typical nuclear statistical equilibrium. So here's just some average mass and charge. For example, just look at the last row. So 40% proton fraction, average mass was 190, the average charge is around 77. And that's in remarkable agreement with a typical nuclear statistical equilibrium calculation based on a finite range droplet model mass formula. So I've got a very simple way of reproducing, at least as long as the temperature is not too low, nuclear statistical equilibrium models. Okay, so that's a start for nucleosynthesis. So we have the simple microscopic model that also works at higher densities where you have the complicated nuclear pasta. And so we can think about calculating the initial conditions for nucleosynthesis, how the temperature evolves, and there are a variety of weak interactions going on which may be changing to some extent the proton fraction. What are the neutrino wind going through this stuff, for example, doing to the composition?
Depending on the trajectory, does it remember anything about its initial composition? If I were, is there an intermediate state that actually raises all of the initial?
So we've expanded the box at different rates. If we expand too fast, the composition changes. But if you expand slow enough, it stays in equilibrium, and then if you expand even slower, you get the same composition.
The astrophysical timescales are fast or slow?
The astrophysical timescales are milliseconds. A millisecond is 10 to the 20th Fermi over C. I work very hard, and I could simulate for 10 to the 8 Fermi over C is a real long time. My dynamical time step is 2 Fermi over C. So doing 10 to the 8 MD time steps is long for me. So we're a trillion times too fast.
Did you correct the FRDM nuclear energies for Coulomb and
Yes.
other effects? Okay.
Yes. Okay. So we have this nuclear pasta to start with, so I wanted to switch gears a little bit. I know lunch is getting close. Not a good slide. I've got two problematic slides in this whole talk, at least. One is the neutron star radius, and now this one in lunch. So I'm interested in observables that may be sensitive to these complicated nuclear pasta phases. So one thing is coherent neutrino pasta scattering. So the neutrino opacity can depend on the complicated shapes. The shapes, the sizes of the shapes are very comparable to neutrino wavelengths. And so we've been calculating static structure factors and even dynamical response functions to look at neutrino pasta scattering and the neutrino opacity in a supernova. Coherent electron pasta scattering gives the mean free path of an electron. The electrons carry the momentum, the energy, and the charge. So electron pasta scattering helps determine the shear viscosity, the thermal conductivity, and the electrical conductivity of the pasta in neutron star crusts. You could have hysteresis in these complicated shapes or in the proton fraction that's appropriate for nuclear pasta in beta equilibrium. And so that could give a bulk viscosity that might be important for damping of our mode oscillations. If you take a box full of pasta and you deform it a little bit, we can get the shear modulus of the pasta. And if you deform the box a lot, you can try to break the pasta. So how strong is nuclear pasta? That's actually work we're just starting to do. How disordered is the nuclear pasta? So Jose Pons et al. Speculate in a recent Nature Physics paper that what they call impure nuclear pasta may have a low electrical conductivity. So the impurities reduce the electron mean free path, giving you this low conductivity, and that could lead to magnetic field decay in neutron stars. Okay? Which is this as controversial as neutron star radii?
Yes.
Okay,
If
good.
you want. So the caveat, which Jose is now stating in public, is that he never includes the core. So if you include the core, you've got high conductivity in the core, the field is frozen and he gets no evolution. So I think
I think there was a caveat that the magnetic field that's supporting the star is in the crust.
Yes.
And I think it's
entirely in the crust.
it's self-consistent, at least the part I understand, is that if the currents are higher levels in the crust, then they'll be driven down to higher densities. So they get to the pasta region.
That's right.
So we can put a, okay. So I'm just trying to understand what could possibly be meant by impure nuclear pasta. Could you have pasta which gives a low electrical conductivity? Okay, so these authors assumed basically a crystal lattice of some average charge, and then they have random impurities. They change the charges of different pieces of pasta at random to get disorder, to get the low electrical conductivity, the short electron mean free path. Couple things to say. One is that if the electron mean free path is low here, it likely could also decrease the thermal conductivity of the crust. And so that may be observable in X-ray light curves when you accrete for a while, heat the crust, and then you can watch the crust cool. Okay, how do you describe possible amounts of disorder in pasta? And could it be large enough to give these low electrical and or thermal conductivities.
Before you go on,
Uh-huh.
point of clarification, I mean, they're very different systems, but there are X-ray pulsars much longer than 20 seconds. I mean, the ones in high mass X-ray binders, there's ones greater than 1,000 seconds. So just
Let me not defend Jose.
I'm just putting it up. I just don't want people to get the impression that there are no pulse neutron stars faster than 20 seconds. There are many.
Slower than 20
That's
seconds.
not slow.
Yes, yes.
So I should say isolated X-ray.
Isolated, I think, was important. Isolated. I mean, certainly there are recycled things. And at any rate, I just want to try to understand, could pasta be disordered, what that might mean. So how do you describe pasta imperfections? I think impurities are unlikely. Nucleons can flow in and out of pieces of pasta, so it doesn't keep its same wrong charge. Instead, an alternative is topological defects. You can have configurations, and I'll show you one in just a second, that could be very long-lived. And maybe the simplest way to do it is just to show it. So this is a simulation, 75,000 nucleons. I started with random configurations and just cooled it down, just let the system evolve. And what happens is they rapidly want to form lasagna, so these flat planes, and you're seeing contours of the proton density. But the system, if you like it, frozen into this configuration. There's a single screw defect. So you have little spaghetti-like pieces which wind around and connect to the lasagna. So this configuration formed in about 1 million Fermi over C, and then it's very stable. It just stays like that for at least 30 million Fermi over C.
So you get equal numbers with the opposite handedness? How does parity work?
I will check the handedness. I apologize, I didn't count. So this is just one single screw defect. Here's another example. It's really hard to see this one. You have a lasagna plane, so I colored those in yellow. And then here's a screw defect, but this thing actually formed a two-dimensional sheet of shear defects. And maybe the easiest way to see this is I printed it out. So here you've got lasagna planes, and then the middle of this is the plane of defects. And this is just the one single screw lattice. Okay. So that at least is something to think about. We are going to calculate how defects like that change the electron mean free path. So that scattering calculation, we're just starting.
I have a question about the two systems. So the magnetar probably experiences higher temperatures where transport is relevant. And the neutron stars are between 10 to the 7 and 10 to the 8 Kelvin. Is that correct? So to explain this discrepancy, do we need the thermal conductivity to be, and the electrical conductivity to be a very rapid function of temperature? Can you then make peace with both?
Well, I mean, certainly disorder is in general more important at low temperature than at high temperature. If the normal thermal scattering is big, then you don't worry about the disorder.
Right. So that's really why I'm asking whether these systems are demanding a high temperature, low conductivity, but a low temperature, high conductivity.
Yeah. Let me just say, my semi-classical model doesn't work really well at very low temperatures. The things I'm passing out are at 1 MeV temperature, so these are relatively hot. Yeah, careful. And they're also very dense. If that was to scale, it's a billion tons.
But I think the hottest accreting neutron stars are not that different from these isolated ones. Okay. In the sense that by the time you wait 10,000 years or so, the core temperature is it's not going to be significantly greater than 10 to the 8. It's not going to be 10 to the 9. You're not talking about cluster systems of 10 to the 9 and then the other
Okay.
ones of 10 to the 8.
So the magnetars are also at 10 to the 8.
It's somewhere around there. I mean, it's not dramatically different.
How am I doing on time? We started.
I think we started about half an hour late.
Oh gosh.
So
Um,
we have another 15, 20 minutes.
Okay. Well, I'll try to use less than that. I wanted to say a little bit. Certainly the outer crust, but maybe the inner crust at lower densities where you don't have pasta. We have nice plasma crystals of ions. So the interaction between ions is again this screen-Coulomb interaction. You can form dusty plasmas in the lab where you can have micron-sized microparticles that get charged up, and then if you cool the system down, you can actually form a plasma crystal of these microparticles, and it's easiest to do that in microgravity. So there's an experiment on the space station, and I showed this just because these are not computer simulations. This is actual data. There's a laser scanner that records the X, Y, and Z positions of each of these microparticles, and then you can watch the system undergo a phase transition, for example, from liquid to solid in complete microscopic detail. And then in the interior of cold white dwarfs, you wait long enough, they crystallize, and when they crystallize, the melting temperature of a white dwarf depends on its composition, the ratio of carbon to oxygen in the core.
What's the neutralizing background in the...
So there's actually a weak conventional plasma in these, between the micro
I see. So
particles.
The interaction is like a screen to cover.
Yes, and you can tune the amount of screening to get different screening lengths. Okay, so I think that neutron star crust is actually an extremely good crystal that is remarkably free of defects, such as vacancies or dislocations, because these imperfections diffuse very quickly. So I think it's a nearly perfect solid that's very strong. And so I'll give you a little bit of evidence why I think that. So I did a simulation for pasta, and I got these long-lived topological defects. I tried to do the same thing for ions, and I start with a liquid, which is an amorphous mess, and then quenched it. So I basically instantly reduced the temperature by a factor of 3. So you get a liquid that's way too cold. But even so, the ions move around enough. So if I just simulate this amorphous mess for long enough, it spontaneously crystallizes.
These ions are all of the same Z, or
These are all of the same Z, but I've also repeated this with impurities, and the impurities don't matter much. So the ions diffuse relatively quickly in this solid. And one of the reasons they diffuse quickly is they have soft 1/r Coulomb interactions. There are no hard cores. There are no electron clouds of each ion to overlap. So ions can get a little closer to each other and slip past. So the stuff diffuses quickly, and so that suggests that white dwarf interiors and neutron star crusts are remarkably perfect crystals.
Can you say more about the impurity simulations that you've done?
Whatever distribution you'd like of charges, we can just put that in to a molecular dynamics simulation. So we can assign individual charges to each of the ions. And we've done simulations all with the same charge, with just small amount of impurities, or with huge numbers of impurities.
What fraction of impurities?
So the impurity parameter, this Q, can be 0, it can be a few, it can be 30, it can be as much as would be appropriate for a liquid.
And you've simulated all
Yes. If the impurity parameter is too big, you can actually get phase separation, where the high Z ions freeze out to a different phase than the low Z ions. But you always get good crystals. Okay. And then, this is a little bit old slide, but the basic idea, we can observe crust cooling, neutron star accretes for a while, and then time zero is when the accretion is observed to shut off, and you observe the decrease in the surface temperature as a function of time, years since the accretion stopped, and the stars cool relatively quickly. That's consistent with a crystalline crust. If the crust were amorphous with a low thermal conductivity, it cools much too slowly. Okay, so we think that at least the outer crust of a neutron star is a remarkably good crystal. If you want a strong continuous gravitational wave source at LIGO frequencies, that places extraordinary demands on neutron-rich matter. Basically, you're going to stress it to the limit. You want a good gravitational wave source. Take a mass, you put it on a stick, and you shake vigorously. That part is perhaps easy. You may need both a large mass. It seems that everybody has observed that. But I claim that in addition, you also need a strong stick. And so that's the part I want to talk about. So a mountain on a rapidly rotating neutron star efficiently radiates gravitational waves. How big is the mountain depends on how strong a stick to hold up the mountain. Okay, the strength of the crust depends on how the crust breaks, so you have to break it. And we've done large-scale microdynamic simulations of how the crust fails. And maybe the easiest thing is to show how normal stuff fails. So this is a molecular dynamic simulation of silicon, and it fails by fracturing. A small crack forms, the crack opens into a void, so if you're stressing the system, for example, pushing on here compared to there, you open this void, and the system kind of opens up like a zipper. And so you break the two things apart. Neutron star crust does not fail like this. It does not fracture. The reason it doesn't fracture is it's a very high pressure. So here's one of our simulations. This was done with Kai Kadao. There's 1.7 million ions. And just as an example, Kai created a defect. He basically drilled a hole through the sample, and you can just barely see the hole right there. And now to stress the system, he's going to push on a frozen layer of ions at the top to one side and this to the other side. And as the system starts to deform, when the lattice is deformed, he will show the deformations in red. So if you start pushing on the system, not surprisingly, it starts to break where that defect is. Whoops, let's try this again. But the high pressure holds the system together. It doesn't fracture. And the only way to finally get it to yield is you have to deform large regions of the crust. So the crust is very strong. To get it to break, you have to bodily deform lots of the crystal. And here's another example. This is 13 million ions. There are 8 microcrystals of random orientations. And Kai did this simulation just to check. Maybe the grain boundaries between these crystals could be very weak, and maybe it fails by adjacent microcrystals basically disconnecting. But again, the system's under high pressure, so you can't disconnect. Whoops. So first you annealed the system for a little while. The frozen layer, you start to stress. It starts to break along the boundaries or start to deform. But again, to get the thing to fail, you have to deform large regions. So these grain boundaries don't change the strength very much. So the bottom line is we find the crust is very strong. To get it, or you can deform the crust, the fractional deformation is the strain by perhaps as much as 10%. Before it fails. So conventional materials fail by fracturing. Plasma crystals are very strong because the large pressure suppresses the formation of vacancies and prevents fracture. And you have these long-range Coulomb interactions. So each ion interacts with thousands of its neighbors, and if you like, you have lots of redundant bonds that give strength. So even if you have defect planes with a few missing bonds, there are neighbor bonds to hold the thing together. Okay, and this strong crust can support neutron star ellipticities. So this is fractional differences in the three principal moments of inertia of a neutron star up to about 10 to the minus 5. Of course, this number is small even given our strong crust because you only have a thin layer of crust. Most of the neutron star is the liquid interior. Let me, in view of time, I just wanted to say a couple things about gravitational waves. So I wanted to talk about searches for continuous gravitational waves rather than burst sources. Okay. These searches are computationally intensive. There are lots of different interesting neutron stars. You could look for fast rotating stars. You could look for stars with large accretion that gets lots of angular momentum that you might want to radiate away in gravitational waves. You could look for young and bright objects. You could look for unknown neutron stars. So most of the neutron stars in the galaxy are unknown, but you could see them in gravitational waves. You could look for unexpected neutron stars. I have two favorites here. I like low mass neutron stars. So if you have a neutron star only weighs a solar mass, because of the lower mass, you can have much bigger deformations, much bigger mountains. Also, there could be exotic solids. So gravitational waves probe the shapes of astronomical objects. Solids keep their shapes. If you have exotic high-density solids, that could support even larger deformations than my strong crust. And so here's one example. This is a search for continuous gravitational waves coming from the galactic center. The gravitational strain depends on the distance to the source. The frequency, so the frequency of gravitational wave radiation is twice the rotation frequency of the star. It's quadruple radiation. Gravitational constant, which makes life so difficult. The moment of inertia of the star is largely known. The only unknown here is the ellipticity. So you're probing the quadrupole moment of the rotating neutron star, and that's the moment of inertia times the ellipticity. Okay, so this search used data from the LIGO 5th science run. Their sensitivity, so they didn't find anything, and they, the excluded region is above these points. Strain as a function of frequency, it's about 10 to the minus 24. So the 4-kilometer arms of LIGO are changing by this silly number, 1 part in 10 to the 24. And this upper limit on the strain corresponds to limits on the ellipticity of 10 to the minus 4 to a few 10 to the minus 5. So this search is not yet quite sensitive enough to see neutron star crust mountains even with our strong crust at the distance to the galactic center. So this is 8 kiloparsecs. But if there was some exotic high-density solid, some quark crystal, that could allow you to have a bigger deformation, and you could have probed such an object. And then, of course, with advanced LIGO, you'll extend the search to lower ellipticities.
I just wanted to comment that for nearby pulsars with the known frequencies that are somewhat in the higher region,
Yes.
the ellipticity limits have been reached up to the order of 10 to the minus 8 or so.
Yes, yes. I mean, there are a number of different searches. I just wanted to give one simple example that I could explain in one slide. The very last thing, and I better be quick, people are getting really hungry. The very high density part of the crust contributes most to the mountains, but the high density part is where the pasta lives. So the actual ellipticity that the crust can support may depend in important ways on the strength of pasta. So right now we're trying to bake pasta, and I can just give you one little sample. So I should explain, the soundtrack is due to a good undergraduate, Emily Clark. There's a microphone at the center, and she just calculates the density in that small region at the center, and that's one stereo channel. And there's another microphone at one of the corners with periodic boundary conditions. All the corners are equal, and that's the other stereo channel. And we were hoping to get a big bang when the sample broke, but this is work in progress. The last thing I wanted to show is this is just the movie Blissfully without the sound, but just if you stretch it a lot, so you're actually stretching the box in one direction, compressing it in the other two to keep the volume the same, and the pasta has to respond, and it does so. And if you think of rubber bands, at some point the rubber bands snap. So this is work done by a graduate student, Matt Kaplan, and this is just our very beginning. We're trying to study the possible strength of some of these pasta configurations. Okay, thank you very much. I'll stop there. Happy to take any more questions.
Still have time for a few questions? So, yeah, you gave a number for the ellipticity, but that was for isolated neutron stars, not
Yes.
merging neutron stars. So how might that change for merging neutron stars? You're talking about hard equational state, but they could be stiffer or softer.
So the question is, what happens to the crust as the star is merging? When does the crust break? And that turns out to be a pretty complicated question. Originally somebody said, well, it gets hot enough, everything just melts quickly and it's all gone. Other people talk about resonant chattering of the crust.
We don't hear about it.
Yeah, I can calculate the microphysics. So if you say you have some region of the crust with some density, some temperature, some stress on the crust, the molecular dynamics can figure out how it responds. And then we have to decide.
So we just look at the direct tidal strain on the neutron star body. Nothing catastrophic happens if you believe that the breaking strain is 0.1 until you're like several kilohertz. So it's either extremely close to merging or already merged. So it's not clear whether you get a direct tidal break or a direct tidal fracture.
So the tidal forces can deform the crust a lot,
Yeah.
potentially before it breaks.
You don't have to worry about mountains because you have a giant
Yeah.
quadrupolar tidal field, right? So.
But some of us also worry about the merged object, how much electricity that might be able to
The
sustain.
merged object is probably
Too hot.
That's what worries about,
Yeah. So
How long it may take?
it's interesting though, if the merged object is going to be stable,
exactly.
then at some point it cools down and the crust freezes, and it's probably in a pretty complicated configuration when it freezes.
I have a question related to that. So we heard that the diffusion properties of the solid make any kind of dislocation. You can smear it out on a fast time scale.
Mm-hmm.
So if you want to sustain a large energy density in anisotropic fashion in the neutron star.
Oh, I mean, the elastic deformation of the crust
Yes.
just stays there. So if you deform the crust to less than 10%, it's an elastic solid, and you just store that elastic energy.
Okay, so you need some other agency like a magnetic field to actually distort the crust.
That's right. I mean, if you stress the crust with something else, you can store that elastic energy in it, and because you can deform the crust so much, I think, you can store a fair amount of elastic energy.
Chuck, is that true? In the sense that normally you talk about either fractures or plastic flow.
Uh-huh.
So what about plastic flow in these systems?
Yeah.
Can you really store this? So more or less, from your point of view, what do we know about that
Yeah.
option?
So that was, there's a couple slides that I skipped. We can only, so the issue is plastic flow under long timescales. We can only
Very long compared
to 10 to the 8 Fermi over C. So Andrei Chuganov and I used a model of plastic flow saying that there was an excitation of a particular size and energy that would lead to the crust breaking. And we fit the parameters of the model to molecular dynamics simulations that we could do, and then extrapolated the model to longer times. So at least within that model, the plastic flow is very slow. So these mountains could last for years. But that's, you have to do a model, and maybe our model isn't the final word.
But is there something one could do a better job at estimating very long time scales? I mean, you in these magnetic field evolution simulations, for example, you have magnetic stresses that exist for a million years,
Uh-huh.
and people just assume that the crust can accommodate that. Is that realistic?
But I think that's not quite true, right? Because if you talk about magnetized flares, you're relying on, in the sort of standard law model, you're relying on some large-scale fracture triggering crustal oscillations was coupled to the magnetic field. So you're relying on, the evolutions allowing you to store up the strain until you get some kind of fracture on the larger scale. Because I think the assumption is still, even though you have a total failure of a very little volume, right? When you average it up to the size of 100 meters, it seems to me it's completely unknown what this means on the larger scale. And so the assumption still seems to be that you need to be able to store that up, otherwise that entire explanation falls.
Well, it's also unclear whether you can get in the magnetized flares, whether you can use the magnetic field to strain in across the direction of the magnetic field, or whether the slipping will just increase magnetic stress, so you can't do that.
Yeah. So how?
So that I think, I don't buy that argument too much, because if you have a twisted torus field, you always have layers where you can build up. It's not a simple saying you can't stretch the field lines like this, but you can always break along the field lines. So if you've got a twisted torus configuration, you've got plenty of that going on.
But how are you going to do that magnetically? How are you going to break along the field line magnetically?
I don't break magnetically. It's the elastic strain that gives.
Let me, there's a lot of complicated issues. So the only statement I want to make is potentially the crust is strong, so it could anchor magnetic field configurations with considerable stress. That's basically all I can say.
But the stress, I can suppose, is a function of the time I ask it to be supported. So there are models of plastic flow, for example, where you have some hopping probability or something.
Yes.
You see, right? So to what extent can simulations like this inform?
Yeah. So I the best I can say is this paper with Andrei Chuganov where we use a model to predict the strength at different flow rates, so or over different timescales. But there's no perfect solution. This has got to be. These are extremely complicated questions, and determining them for conventional materials is extraordinarily hard. Fortunately, the crust is maybe simpler than a conventional material, but it's still very hard.
I think we should stop here. We'll have time for discussions in the afternoon, and thank Chuck again.